Hello friends, here in this video we will see an expression of normal and tangential stress, that is we are going to derive the formula for normal stress and tangential stress which would be further used in the problems. Let us get started. Here the heading is expression for normal and tangential stresses. Now, see, when we are deriving the formula, for that first I'll draw the diagram. Now, here I have drawn a plane ABCD. I'll say that while deriving the formula, let us consider a plane ABCD. Now, once I have considered this plane, the next thing is I'll denote stresses on this plane. So, on AB, here I'll denote stress along x direction. On CD, also stress along x direction. So, because of sigma x, there is tensile stress developed in this plane. Next, tensile stress along y, sigma y. Then, apart from this, I'll also denote shear stress tau on face CD. It is acting upward. So, for shear stress to be produced on AB, I'll assume the shear stress is acting in downward direction. Similarly, along AD, the shear stress would be towards left. Along BC, it would be towards right. So, after I have considered the plane, I'll say that let sigma x be stress along x direction, and this will be tensile stress as per our assumption. Next, similarly, I'll write for sigma y. Let sigma y be stress along y direction, that is also tensile stress. Next, and shear, or I can say tangential stresses tau, which is acting on the plane. Now, inside this plane, I am taking an oblique or inclined section. I'll call it as, this plane is A suffix E, that is AE is the inclined plane. Its inclination with the vertical AB, that is theta. Now, when we are deriving this expression for normal and tangential stresses, in that I'll consider the oblique section, and we are going to find the normal and tangential stresses on this oblique section or oblique plane AE. So, for that, what I have to do, I'll take this part or this triangle separate and I'll draw it here. Now, this triangle is ABE, right angle triangle, ABE, on which there is sigma x acting along x direction on face AB. Then there is shear stress tau acting downward on face AB. Next, sigma y is acting downward on BE. Tau is acting on BE. Then, apart from this, on the oblique section, there will be one of the stress which is perpendicular to the oblique section, and that would be called as normal stress, denoted by sigma suffix n. Then there will be one stress which will be parallel to AE, and this stress will be called as tangential stress. So now if we see, on face AB there are two stresses, on face BE there are two stresses, similarly on AE there are two stresses. So because of these stresses there would be forces acting on the member, and here this I'll call it as angle theta. So after this I'll say that there are six forces acting on triangle ABE. So from this, first I'll consider AB. So force or forces acting on AB are, now as we know, stress is equal to force upon area. Force is denoted by P upon area. So therefore force becomes stress into area. So here I'll write all the forces in the form of stress into area. If I consider AB, I'll say that let width of plane be unity, that is equal to 1. So here if I am assuming the width as unity, area becomes AB into 1, which is AB. So forces acting on AB, first I am considering sigma x. So because of that the force acting would be sigma x into area is AB into 1, because width is 1, and here we can write it as sigma x into AB. So this is the force acting on AB because of sigma x. Similarly, because of shear stress tau, this tau I'll call it as tau AB. So there is shear stress tau acting on face AB, and the area is AB. So now here I have written forces acting on AB are sigma x into AB and tau into AB, because area is equal to AB into width, and here width is 1. So therefore area is equal to AB. So these are the forces acting on AB. Next, forces acting on BE, that is this side BE. Forces acting on BE are, if I see, first there is sigma y, so sigma y into BE, again width is 1, so area will be only BE. Next there is tau, and it is acting on BE, so tau into BE, area is only BE. Next, forces acting on AE are, as I can see in this triangle, AE is the hypotenuse. So the forces acting, first I'll see sigma n into AE, that is the normal stress into AE, area is AE into 1, so it becomes AE. Next, sigma T, that is the tangential stress, so sigma T into AE. So these are the 6 forces which are acting on the triangular element which we have taken out of the plane ABCD. Now, if we see in the diagram, here we are having right angle triangle and the forces are acting over that. So we are considering the inclined plane, and for us the inclined plane, the parallel component acting upward will be treated as positive x-axis, parallel component downward will be negative x-axis, then the component or the axis perpendicular to the inclined surface, that would be positive y-axis, and here we would be having the negative y-axis. So now we have to resolve all 6 forces based on this component, and here I have resolved it and I'll explain it. Here I have resolved all the 6 forces which are acting on the triangular element. I'll explain them one by one. First we will consider side AB. On this I'll consider the first force, which is sigma x. Now for this sigma x, if I see it here, then if I draw a line parallel to AE, it would be passing through this and perpendicular. So we would be having 2 components of sigma x. Next, the angle here, since this is 90, here there is theta, so the angle here, this becomes 90 minus theta. So here also that is 90 minus theta, and this angle is theta. So here the component here is sigma x, that is the stress, and force, it is sigma x into AB cos theta, because I am resolving the forces. Here it is stress, force is sigma x into AB cos theta, sigma x into AB sin theta. So the first component is sigma x AB cos theta, sigma x AB sin theta. Next, on this face we even have shear stress tau, which is tau AB. So tau AB is the force. Now again, if I draw a parallel component, I will get 2 components of tau AB, and that 2 components are tau AB cos theta, tau AB sin theta, because here it was tau AB, the force, shear force acting on AB. Parallel to this plane I have drawn a line, so this angle becomes theta. So here we have tau AB cos theta, and here there is tau AB sin theta. Next, if I consider the face BE, on this I am having the force sigma y into BE. Now if I draw a line parallel to the plane, here I have a component, this is inclined at theta, because theta is the inclination with the plane with vertical. Similarly for this parallel line to the plane, there is theta angle. So here I have the component sigma y BE, because this is the force, cos theta, sigma y BE sin theta. Next, on this plane we have shear stress tau BE. Now if I draw a line parallel to the plane to this tau BE, here I have this angle as 90 minus theta, which is here. So this component which is perpendicular to the parallel one, this will have an angle theta. So tau BE cos theta, tau BE sin theta. Next, after we have seen faces AB and BE, at last we have face AE. Now the component which is parallel, there is no need to resolve because it is parallel to the plane. So it is sigma t AE as it is. Next, the component which is perpendicular to the plane, that is sigma n AE, it will remain as it is. So here this diagram which I have drawn, it is actually the resolution of all forces acting on right angled triangle ABE. So here I have resolved all the forces. Now by using this diagram, we are going to find normal stress and tangential stress, because as per the derivation we have to find the expression for normal and tangential stress. That is, we have to derive the formula for sigma n and sigma t. So for that we would be using this diagram. Now when I am using the diagram, for this I'll use the conditions of equilibrium, and first I'll go for the formula of sigma n. Now sigma n is perpendicular to the plane, so it would be treated as y-axis. So I am going to resolve the forces. Now I'll say that after resolving this, using conditions of equilibrium. Now when I am using the conditions of equilibrium, I want sigma n formula first. So sigma n is nothing but it is acting along y-axis. So I'll take summation of forces along y-axis is equal to 0, or this can be even said in this way, that sum of forces along y on left hand side should be equal to the sum of forces along y on the right hand side for equilibrium condition. And here the upward forces which are perpendicular to the plane, that is, if we have an inclined plane and the forces perpendicular to it acting upward are treated as positive y and downward are treated as negative y. So as per this convention, we are going to write the forces. So summation of forces along left is equal to summation of forces along right. So we have to see at first the forces which are perpendicular. Now if I see sigma n AE, it is perpendicular. So I'll consider this first, it is acting along positive y. So therefore sigma n into AE. Now if I see out of all the components which are vertical, that is perpendicular to the plane, only sigma n AE is acting upward, remaining all components are acting downward. So on left hand side I have only sigma n AE. Now I am going to write the right hand side. For that, first I have on side AB sigma x AB, the component sigma x AB cos theta is perpendicular to the plane acting downward. So first I'll write this sigma x AB cos theta. Next, here we even have tau AB sin theta acting downward. So plus tau AB sin theta. So now here I have written tau AB sin theta. So on face AB, the two components which are perpendicular to the plane, I have written them. Next, on face BE, here we have tau BE cos theta and sigma y BE cos sin theta, which are perpendicular acting downward, so negative. I'll write down plus tau BE cos theta and plus sigma y BE sin theta. Now here there is no need to take negative sign because we are equating the forces, because if we bring them on one side then we have to consider negative. Since we are equating them, then there is no need of negative sign and the resultant would be equal to 0. Now after reaching this step, I'll say that dividing throughout by AE. Now when I divide throughout by AE, here I have sigma n on left hand side, AE will get cancelled. Here there is sigma x AB upon AE cos theta plus tau AB upon AE sin theta plus tau BE upon AE cos theta plus sigma y BE upon AE sin theta. Next, I'll simplify this, that into the bracket I'll write down, since AB upon AE is equal to, now looking from the bigger triangle, AB is the adjacent side to theta, AE is the hypotenuse, so I'll write down since cos theta is equal to AB upon AE, I'll use this relation, that is adjacent upon hypotenuse, and similarly I'll write down for sine theta, it will be BE opposite to theta, BE upon hypotenuse, which is AE. Now here I have written the formula. So for AB upon AE, it is equal to cos theta, and BE upon AE, that is sin theta. So here I'll replace AB upon AE with cos theta, BE upon AE with sin theta. So this will be simplified as sigma n is equal to sigma x into AB upon AE cos theta. Again we have one more cos theta plus tau AB upon AE, that is cos theta into sin theta, plus tau BE upon AE, that is sin theta into cos theta, plus sigma y BE upon AE sin theta into sin theta. Then it can be written as sigma x cos theta into cos theta becomes cos square theta, plus here we have 2 tau sin theta, I can add them, sin theta cos theta, plus sigma y sin square theta multiplication. Next, after reaching this stage, here I will use again one more formula for cos square theta sin square theta and 2 tau sin theta cos theta. I will write down that into the bracket, since cos square theta is equal to 1 plus cos 2 theta by 2 and sin square theta is equal to 1 minus cos 2 theta by 2, and here sin 2 theta also, sin 2 theta is equal to 2 sin theta cos theta. So I am going to use these formulae and replace them. Cos square theta can be written as 1 plus cos 2 theta by 2. So therefore sigma n is equal to sigma x as it is. Cos square theta I will replace it with 1 plus cos 2 theta by 2, then plus here I am having tau, so I will keep tau as it is, plus tau. Now 2 into sin theta cos theta, that is nothing but sin 2 theta, then plus sigma while I will keep it as it is, sin square theta is 1 minus cos 2 theta by 2. So here I have used the formula and written it here. Next, after reaching this stage, I'll write it as sigma n multiplying sigma x into the bracket. So sigma x by 2 plus sigma x by 2 cos 2 theta. Then here I'll bring this term over here, sigma y by 2 multiplying it minus sigma y by 2 cos 2 theta, plus I'll write it in the end tau sin 2 theta. So therefore from this I'll bring sigma x and sigma y together. So adding these two terms, sigma x plus sigma y by 2, bringing them together. Next, plus from these two terms, as I can see here, cos 2 theta can be taken common, so it can be written as plus sigma x minus sigma y by 2 into the bracket cos 2 theta, because I can take cos 2 theta common. Next, at last we have plus tau sin 2 theta. So this is my equation number 1, and I have got the formula or expression for normal stress. Half of the derivation is done here. I can say that therefore from equation number 1, normal stress on an oblique plane can be calculated. Next, as I have used the first condition of equilibrium to get the formula of sigma n, now I'll use the second condition of equilibrium, that is summation of fx, to get tangential component or tangential stress sigma suffix t. So after reaching here, I'll say that therefore again by the condition of equilibrium, summation of fx is equal to 0, or I can say that sum of forces acting along x on left hand side is equal to sum of forces acting along x on right hand side. And here the parallel plane, forces acting parallel and up the plane are positive, forces acting parallel and down the plane are taken as negative. So now here I am taking the second condition of equilibrium, that is summation of all forces on left hand side should be equal to the sum of all forces on right hand side. Now here if I consider this diagram, in this the forces which are parallel to the plane are along x, which are upward parallel to the plane and upward they are on positive x axis. Forces which are parallel and acting downward they are on negative x axis. So here if I see sigma t into AE, that is acting downward and parallel, so negative. So what I am doing here, instead of writing negative, I am equating the forces on left hand side, right hand side. So there is no need to write negative sign. So sigma t AE, then here we have tau AB cos theta, that is also acting along sigma t AE, their direction are same, so plus tau AB cos theta. Next we have sigma y BE cos theta acting parallel and downward. Now these are the forces acting downward and parallel is equal to the forces acting upward and parallel. Out of them we have sigma x AB sin theta acting parallel and upward. Then we have tau BE sin theta acting parallel and upward. Then here we have only these forces which are acting on right hand side. Now I'll keep sigma t AE on one side because I want the expression for tangential stress. Shift all terms on the other side. So sigma x AB sin theta plus tau BE sin theta, then minus tau BAB cos theta minus, I am sending this term onto the other side, so minus sigma y BE cos theta. After this I will say that therefore dividing throughout by AE. So if I divide throughout by AE, here AE and AE will get cancelled out, so sigma t is equal to sigma x, it will be AB upon AE sin theta plus tau BE upon AE sin theta minus tau AB upon AE cos theta minus sigma y BE upon AE cos theta. Now previously we have seen that since cos theta is AB upon AE and sin theta it was BE upon AE. So here I will replace AB upon AE with cos theta, BE upon AE with sin theta, and writing this equation again. So I have sigma x will remain as it is. AB upon AE, that is cos theta, plus here we have tau BE upon AE, in place of that sin theta into sin theta. Next minus tau AB upon AE is cos theta into cos theta again, then minus sigma y BE upon AE sin theta into cos theta. Now here I have written this equation. Now in that I can write it in this way, that here we have sigma x sin theta cos theta. I'll bring this term here, so minus sigma y sin theta cos theta, then plus here I have tau sin theta into sin theta becomes sin square theta, minus tau cos theta, that becomes cos square theta. So therefore here sigma t will be equal to, I can take sigma x minus sigma y together and taking sin theta cos theta common, plus here in this case as well I can take the term, here I am having plus tau. So what I'll do to write it in a more effective way, I'll take minus tau common, so into the bracket I am left with cos square theta minus sin square theta, because I want to write it in some special form, that is why I am taking minus tau common. Next here I'll be multiplying this sigma x minus sigma y, this term, by 2. So here I have 2 sin theta cos theta and dividing this by 2. So multiply and divide by 2 this term. So once 2 and 2 get cancelled, it is the same thing. Next here I have minus tau. Instead of cos square theta sin square theta, we can write it in this way, that it is cos 2 theta, because the formula is cos 2 theta is equal to cos square theta minus sin square theta. Next, tangential stress will be equal to sigma x minus sigma y by 2. Here 2 sin theta cos theta, that is sin 2 theta, minus tau cos 2 theta. So I'll highlight this equation. This is equation number 2, and I can say that therefore from equation number 2, tangential stress can be calculated. So here I have finished the derivation part, that is we have calculated or we have derived the formula of both normal stress and tangential stress acting on an inclined plane. Now one more thing, this theta is called as the location of principal plane. So I'll find the equation. This is just an addition part, that is location of principal plane. So once we know that principal plane, it is that plane which carries only normal stress and no tangential stress. So for principal plane, tangential stress is 0, because as per the definition of principal plane, it is that plane on which only normal stress is there. So tangential stress will become 0. So I'll say that therefore equation number 2 becomes, here we have in equation 2 the tangential stress, if this becomes 0, because we want to find the location of principal plane, if this is 0, we can write it in this form, sigma x minus sigma y by 2 sin 2 theta minus tau cos 2 theta is equal to 0. So therefore I'll shift this term onto the other side. So here we have sigma x minus sigma y by 2 sin 2 theta is equal to tau cos 2 theta. Therefore keeping sin 2 theta on one side and bringing cos 2 theta in the denominator, Here we have tau upon sigma x minus sigma y by 2. So therefore, I can write this in this form, that tan 2 theta will be equal to, this 2 will go into the numerator, 2 into tau upon sigma x minus sigma y. So here I have one more expression, that I can say that this is equation number 3. So therefore, from equation number 3, the location of principal plane can be found out. So here in this derivation we have seen the expression of normal stress, tangential stress and the location of principal plane. With this we complete the derivation part.